welcome back, everyone. We're really excited to dive back into our GREMax Quant webinar this evening with you. By way of reintroduction, for those of you here for the first time or who have been with us for the whole ride, as always, a reminder, you can hop into the TestMax YouTube channel to see the recordings of past. But for today, I am Jonathan, the head of content here at TestMax. Just by way of background, completed my law degree at Harvard Law, business school at NYU, undergraduate at Harvard as well. Have been working and teaching and tutoring in the GRE for many years now. I love the tests and love working with folks to help achieve their dreams and target scores and get into the grad programs and make the impact they want. So really thrilled to be joined by my awesome colleague, Daniella.
Hi, everyone. My name is Daniella, and like Jonathan, I really do enjoy helping all students gain their desired score of their dreams. A little bit about me. I'm from Los Angeles. I did my undergraduate at UC Berkeley, where I studied business, and then I did a master's degree at Cambridge in public policy. And this upcoming fall, I will be attending a top 10 law school using the GRE. So I can speak from experience that as someone who hasn't succeeded or is not a natural at test taking at first or succeeded at first, that the approaches here really help you tackle all of those challenges. So I'll pass it back to you, Jonathan, as you take us through our lesson today.
Awesome. Well, thanks, Daniella. And that's a fantastic reminder of our overarching ethos and values here, which is we only hire and train and work with folks who were not naturals to the test. So that includes all of us here at TestMax. So what we had to do ourselves is struggle without the best resources and reverse engineer, boil it down to first principles, make it as simple and as comprehensible as possible. And that's what we've built from the ground on up. So if you're looking for a broader overview of the value that the GRE can unlock for you, again, go to that TestMax YouTube channel. We have a really awesome, comprehensive video speaking of the tens of thousands of opportunities and busting some of the myths around what the GRE is for, applying to almost every single master's program, almost every single pre-professional degree and doctoral degree in the United States and even across the world. But with that, today we're focusing in on quantitative reasoning yet again. So as a reminder, these are some of the most common refrains that we encountered ourselves and we hear in working with our students. I'm just overthinking on quant. I'm just running out of time. I'm just not a math person. I'm just not a geometry person. Our brain will find all sorts of excuses. And here at TestMax, at GREMax, we use a behavioral and cognitive science informed approach to our teaching and really hone in on the fact that these are all euphemisms. These are all just sentences running in our minds that stand in for, I haven't yet mastered the quantitative reasoning skills sufficient for my target score. So we talk about this over and over and over again, but the GRE is fundamentally not a math test. It's not a computation test. It's a reasoning test. A reasoning test that uses the language, logic, and syntax of the English language and of high school level mathematics. So with this as our preface, today we are diving into a subsection of algebra, right? So there are four big substantive areas: arithmetic, algebra, geometry, and data analysis. And within the algebra subsection, we're honing in on inequalities. As always, throughout, we have the Q&A, we have the chat. We're really here to be of service to you. And so we want to hear what your grad school aspirations and dreams are, why you're here, what value you're seeking to get, any questions, any follow-up. And that goes throughout the lesson, throughout the real, actual GRE questions we'll go through later on this evening, and about anything else. So with that, let's dive right in. Okay, let me move the speaker screen out of the way. Let's see, let's minimize that. Okay, fantastic. Inequalities tell us about the relative size of two or more values. So oftentimes in algebra, we're used to seeing equal signs, where some expression or some value equals another. Sometimes, however, we only know or are given that something is greater than or less than, or greater than or equal to, or less than or equal to something else, some other value. So as we know throughout the GRE, we're going to have fluidity in translating between words, numbers, values, variables, and the like. So let's look at a simple example to start us off. Alex and Billy have a race, and Billy wins. Well, what do we know? We don't necessarily know how fast they ran, but we do know, in this case, Billy was faster than Alex. So just one way of expressing and translating the words or the word problems we'll encounter in many scenarios to a simplified expression using an inequality, where B, in this case, might substitute for Billy our inequality sign greater than, and A substituting for Alex. So we like to keep it as simple, as clean, as structured, as organized as possible. All right. As a brief reminder and a refresher of this inequality sign, right? What is greater than, what is less than? If we ever get confused, the bigger side, the open side, the sort of Pac-Man side, right, is indeed the side that is greater than the other. The other side being smaller or less than. All right. One thing, one value, one expression can be greater than or less than another, but indeed we use these symbols to indicate they can be greater than or equal to, or less than or equal to. So using another simple example, you must be 13 or older to watch a movie. The relationship, the inequality being drawn is between one's age and the age of 13, the age at which you may be able to watch this movie. So let's say we simplify this to age must be greater than or equal to 13. We always start out simple, foundational, break it down. What are the fundamental tools? And then we ramp up. So here we go. Okay. Just trying to move our faces out of the way. Our aim is to have X, or whatever the variable is, some letter that stands in for some number on its own. We like to isolate it on, say, the left side of the inequality sign. So let's say we're given this expression. X plus 2 is greater than 12. Intuitively, and we see this over and over again, both on quant and in verbal, we want to translate, break it down. The GRE, the test maker, loves to play on our cognitive biases, our shortcuts, what our untrained mind might jump to in assuming. To overcome that consciously, we simplify expressions, we boil them down to make them easier to work with. So indeed, in this case, X plus 2 is greater than 12. We can manipulate it or change both sides in a similar way, although we'll see the caveats in just a moment, as we would with an equal sign. We subtract 2 from both sides, and indeed we find X is greater than 10. All right. Certain manipulations or changes do not affect the direction of the inequality. Those include adding or subtracting a number from both sides of a single inequality, multiplying or dividing both sides by a positive number by a value that is greater than 0, or simplifying a side. So let's look at this particular example. 3x is less than 7 plus 3. In this case, we can simplify the inequality, indeed add the terms on the right-hand side, and find that 3x is less than 10. we can then isolate the x even further, divide both sides by 3 because 3 is positive, 3 is greater than 0, and find that x is less than 10/3. We'll look at, again, some caveats in just a moment. Okay. However, critically, certain things, certain changes do change the direction of the inequality, where a greater than sign becomes a less than sign, or a less than sign becomes a greater than sign when we multiply or divide both sides by a negative number, a number less than 0, or if we're just looking at an expression in a different way, if we're swapping the left and right sides, but less important for consideration. So for instance, just again, beginning with a simple example, if we see 2y plus 7 is less than 12, well, of course, that is the same as saying, hey, 12 is greater than the other side, 2y plus 7. All right, so let's take a look at another example. X plus 3 is less than 7. So we want to isolate the variable, keep it on its own, subtract 3 from both sides, and indeed we find x is less than 4. So we're going to visualize, we're going to have a lot of different tools in our toolbox, building on the fundamental rules. One of those tools will be the number line, which will be super helpful on the real question, the real GRE questions we'll deal with at the end of today's lesson. So we subtracted 3 from both sides of the inequality. What do we do on the number line? So here we're looking at the positive side of the number line and 0. And what we see here is we had this green line go all the way up till 7, but it didn't include it. And the way we express that on a number line is with an open circle. The way we express a value being included on the number line is with a closed circle. So that's what it would be if it said x plus 3 is less than or equal to 7. So when we color in or close in the circle or dot on a number, that signifies, hey, it's included. It's part of the set of numbers. However, here it's strictly less than 7. So as you can see here, 7 is not included. Okay, x plus 3 is something. We don't know what it is, but whatever that something is, you can think of this number line like an accordion, right? You're setting the bounds of what that something is all the way up until it hits the wall where x is equal to 7. Hey, stop there. No more. All right, but when we subtract 3 from both sides of the inequality, and indeed we find x is less than 4, all right, that wall or that side of the accordion is being squished in towards 0, and indeed the wall hits at 4. Again, this time not including 4 because it says x is less than 4, not x is less than or equal to 4. Okay, so remember that important caveat. We said, hey, when we multiply or divide by a negative number, we have to be very careful and flip the sign. Well, why is that? Let's use the number line to demonstrate this. So we have to reverse the inequality when multiplying or dividing by a negative number, because take a look at the number line. When we go from 3 to 7, that is an increase. When we go from -3 to -7, that is a decrease. So notice that when we go from on the positive side of 0, right, values that are greater than 0, and we go from, let's say, x is equal to 3, all the way hopping along to x is equal to 7, we find that, well, hey, we got to a bigger number. However, when we flip over, mirror over the 0 on the negative side of the number line, and we go from -3, and we hop along all the way to -7, Well, what have we done? It is more negative. So the value has actually decreased. So on the number line, when we compare different values, they're increasing from left to right. So as we become more negative, this value is indeed decreasing. So this is one other way of visually depicting on the number line why we have to flip the inequality when we multiply or divide by a negative number. Think of it as flipping it over the mirror. And so it's the mirror or the inverse of what you had on the positive side. Okay, now we're going to integrate, right? This critical caveat, hey, multiplying or dividing an inequality by a negative number, flip the sign. Why? Because on the opposite side of the zero on the number line, it has the opposite effect. It becomes more negative. When you go from 3 to 7, it gets bigger. But when you go from -3 to -7, it gets smaller. So let's take a look at an example. -2y is less than -8. All right, simplify, 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 isolate the variable when at all possible. So let's divide both sides by -2. And indeed, we find that -8 divided by -2, 8 divided by 2 is 4. The two negatives cancel out to a positive. So the right-hand side is simply +4. On the left-hand side, -2 divided by -2, 2 divided by 2 is 1. The negatives cancel out, so it's positive. But what happens to the inequality? Well, we said we have to reverse the sign of the inequality, right? When we're flipping an expression over the neutral zone, and we're going from negative to positive or positive to negative, indeed we find that what was -2y is less than -8. Remember, it's smaller as it gets more negative. Well, it gets bigger as it gets more positive. So y is bigger than 4. You multiply or divide an inequality by a negative value. Hey, apply the same to both sides like you would with an equal sign, but you've got to flip the inequality. Okay. Now, let's add another little wrinkle, because we know the GRE loves different wrapping paper for the same stuff. So oftentimes we'll be presented with multiplying or dividing by variables. No stress, same stuff, different wrapping paper. What's a variable? Just some letter, something that stands in for some number. Unless you're given an explicit constraint, remember the test maker wants you to make the unwarranted assumption that, hey, x has to be positive, or hey, x can't be 0, or hey, x isn't a fraction. Because our mind might default to, let's say, a positive integer. Well, unless it's explicitly defined, don't assume it. So here, we're multiplying or dividing by a variable. In this case, we have bx is less than 3b. Again, we're just looking at simple building block examples. We'll look at real questions in just a moment. So the untrained mind might say, all right, let's just divide both sides by b, right? Isolate, simplify, get x alone. Well, if we divide both sides by b, indeed the b's cancel out, so you get x is less than 3. But wait, we just saw an example where that b was -2. And what happens if we multiply or divide by a negative number? Again, we have to flip the inequality because we're going over the neutral zone. We're going over the 0. What would get bigger on the positive side is now getting smaller, more negative on the negative side. So in this case, if b were negative, we'd have to reverse the inequality. Is x bigger than 3 or is x less than 3? Those are mutually exclusive answers. Well, indeed, we don't know if b is positive or negative unless we're told. So we can't answer this one, or we can't determine what the values would be for x. All right. Sometimes the GRE will say, hey, we're giving you 2 inequalities in one, or multiple inequalities at once. All right, have no fear, no stress, same stuff, different wrapping paper. So we're told 6 minus 2x all over 3 is less than 4 and greater than -2. All right, so using our tools and skills from algebra, simplify, 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 and isolate the variable when possible. We're going to say, first, let's multiply and carefully distribute that number across every value in the expression by 3. So that means you're multiplying the -2 by 3. You're multiplying the middle term, 6 minus 2x by 3, 6 minus 2x over 3 by 3, and the 4 by 3, right? We have to distribute it to every term fairly. Okay. We're multiplying it by a positive number, so the inequalities don't change. We've just gotten rid of the denominator in the middle term. Great. Now, let's subtract 6 from each part of this compound inequality. So we take -6 for the middle term, -6 from the leftmost term, and -6 from the rightmost term. Notice how being careful and systematic and organized with our signs will be key, because you can bet on there being a trap answer for the test taker who doesn't account for, just looking at this example, -6 minus 6. It's becoming more negative, -12. Being very careful with our signs is key throughout. Okay, so let's say we've distributed 3, subtracted 6 from every part of the expression, and we find -12 is less than -2x is less than 6. All right, we want to slow the mind down when it comes to inequalities and negative values being multiplied or divided. We want to, hey, pause for a moment, something's going on. Recall, the sign flips when you multiply or divide by a negative number. Why? Why does this have bearing here? Let's start taking it piece by piece. Divide each part by 2, right? Breaking it out because -2 is equal to 2 times -1. So let's see the effect each part alone. Here, we're going to divide every term by 2. We'll find that -x is less than 3 and is greater than -6. Again, distributing that 2 across each term. All right, now we're going to divide or multiply, it's the same effect, by -1. Again, distributing across each individual term, but this time we flip the inequalities. Again, recalling, we're mirroring, we're flipping over the neutral zone, so the effect of what would get bigger on the positive side gets even smaller on the negative side. So we divide or multiply every term by -1. -x times -1 is x, -6 times -1 is 6, and 3 times -1 is -3. And we flip the less than sign, each less than sign, to a greater than sign. Now, integrating all of our fundamental rules together, we can just express this equivalently in a cleaner, easier to see way, which is generally from left to right. So x is bigger than -3. And you can even, in your own mind, say this to yourself, because it's very easy. What seems very simple can get very tricky when you have a minute and a half and you're trying to deal with the signs and flipping the inequalities. And that's where you don't want to get hung up. So when you're reading this expression, you're saying, hold on, x is bigger than -3. Okay, I can express that as -3 less than x. X is bigger than -3. -3 is less than x. X is less than 6. Oh, okay, cool. That's familiar to me. Left to right, easier, simpler, fewer mistakes. All right. So we'll also be integrating on this number line. We've looked at some of the fundamental rules of inequalities, and especially critically, what happens when you multiply or divide by a negative number. Flip the sign. Now we're going to look at some absolute values, and then we're going to transition into real, actual GRE quant questions that will pull together the absolute value concepts and rules and the inequality concepts and rules. Okay, so we have this same number line, right? And with the absolute value, what these two bars indicate to us very simply is, hey, how far is that value, or how far is that number from zero? Zero is this very powerful center point, this neutral point. It's neither positive nor is it negative. So in this case, we're taking the value of 6. So how far is 6 away from 0? So we can literally count it. 1, 2, 3, 4, 5, 6. Cool. The absolute value of 6 is 6. How far is that number or that value from 0? Okay, what about negative 6? Okay, well, we're mirroring, flipping over that neutral 0 line, and we're saying, how far is negative 6 from 0? Well, it's 1, 2, 3, 4, 5, 6. Oh, it's the same thing, of course. Absolute value, the distance of the number from 0. Indeed, the absolute value of 6 is equal to the absolute value of negative 6 because the distance is 6. All right. So in more general terms, we find that the absolute value of x is equal to x itself, as we just saw. The absolute value of 6 is equal to 6 when x is greater than 0. The GRE loves playing on positives and negatives and zeros, or integers and fractions, or less than or equal to. These dichotomies or trichotomies, and we have to have crystal clear categories in our mind. So note, the absolute value of x is equal to x when x is greater than 0. If the rule gets tricky or isn't as sticky, pick easy numbers. Hey, remember I saw that example? Absolute value, distance of the number from 0, well, the absolute value of 6 was 6, so it's itself. So yeah, the absolute value of x is x when x is greater than 0. The absolute value of x is equal to 0 when x is 0. How far is 0 from 0? 0. It is there. It is 0. The absolute value of x is equal to negative x, however, when x is less than 0. Again, you can pick easy numbers and prove it to yourself on the number line. You can literally draw it out in your notebook to gut check the rules as you go throughout practice. Again, recall the simple example, the absolute value of negative 6. How far was negative 6 from 0? It was 6 away. Just like 6 was 6 away from 0. Oh, 6 is equal to the negative of negative 6. The negative, the double negative becomes a positive. When, and this applies when the absolute value of x is equal to negative x, when x is less than 0. Super, super valuable, helpful framework that, again, we don't have to stress about, but rather we can intuit and rederive and see it come to life in practice. And whichever way of presenting works best for you, go for it. Whether you like the algebraic expression of the rule, whether you like the visual on the number line, whether you like the intuition of picking numbers. These are all different tools in the toolbox, different ways of presenting the same fundamental relationships, whatever is stickiest and most effective for you. Okay, a couple of properties of absolute values that can be helpful. Again, and this is a super helpful skill, both on verbal and on quant, is forcing your mind in active reading, because every part of the GRE is a reading test. Translate, break it down, simple as possible. So even when I'm seeing absolute value, I'm like, oh, okay, distance from 0. Okay. First property, the absolute value of A, some term, some value, is always greater than or equal to 0. Well, why is that? The distance from 0 can only be 0 if a is 0, or something greater than 0. How far do you have to walk? Take a hike from 0? Well, you're going to hike this way, or you're going to hike that way, or you're going to take a seat on 0. Either way, the value is going to be bigger than or equal to 0. Okay, this one's a little bit trickier, less common, but important nonetheless. The absolute value of a, some value, you can call it x, you can call it a, you can call it apple, is equal to the square root of a squared. Squaring a, squaring some value, makes it positive or 0. And then taking the square root will, quote unquote, undo the squaring, but leave the value indeed positive or 0. The absolute value of a times b is equal to the absolute value of a times the absolute value of b. Sometimes breaking apart or recombining different absolute values can be helpful. And let's look at this final example. Again, just different values, different variables standing in for different values. In this case, the absolute value of u is equal to a is the same as saying u is equal to plus or minus a. So we'll look at this in an example in just a moment. All right, we're solving this. We are solving this equation. The absolute value of x plus 2 is equal to 5. Well, if the absolute value of something is equal to something else, well, that's like saying, hey, whatever is in the absolute value is equal to plus or minus the value it equals. So when I'm given the absolute value of x plus 2 is equal to 5, I'm setting up two different equations. X plus 2 is equal to 5, which I then simplify, subtracting 2 from both sides, and I get x is equal to 3, or we can use the v to signify or x plus 2 is equal to negative 5. Again, being very careful with our signs here, subtracting 2 from both sides, x is equal to negative 7. So we have two possible solutions or two roots for this equation. Okay, so let's look at this visually as well as numerically on the number line. So we're told the absolute value of x is less than 3. Recall again, the distance of x to 0 must be less than 3. Well, let's start with the easy side. Let's start on the positive side. Well, if the distance from x to 0 is less than 3, then again, using our notation of the open circle on 3, which means we're excluding everything 2.99999 ad infinitum all the way up to, but not including 3. And all the way down to 0. Starting out on the positive side, hey, the distance from 0 is less than 3. So that covers 1 hop, that covers 2 hops, and that almost covers the 3rd hop, except it stops at 3. But also, because the absolute value refers to the distance of x from 0, we got to look at the mirror, or the flip side, the negative land. In negative land, remember, it's the mirror, it's the flip. The distance has to be less than 3, so that covers 1 hop, 2 hop, and up to 3 hops, but it stops, right? We have that open circle on that 3rd hop, on the negative 3. So, indeed, another way of expressing this is x is less than 3 and greater than negative 3. All right, let's pre-integrate these two into another inequality. The absolute value of 3x minus 6 is less than or equal to 12. So using the same principle, we keep the meat, we keep the stuff from the absolute value, and we say, okay, on the positive side, it's going to be less than or equal to 12. Cool. So this is the same exact thing as what we see here. But also, remember the absolute value of u is equal to plus or minus a. This is going to be greater than or equal to negative 12. Take that flip side, flip the inequality of the negative. So whatever's in the absolute value is going to be less than or equal to whatever the value is here. It's 12. Or it's going to be the flip of that of the negative value. Or in this case, greater than or equal to negative 12. Recall again, because the absolute value just tells you, hey, what's the distance from 0? Well, hey, the distance from 0 here of whatever 3x minus 6 is has to be less than or equal to 12. So you can redraw the number line either in your mind or on paper. So we're doing the tick marks, let's say all the way up to 12. So recall, the hops is going to cover 1, 2, 3, all the way up to, but not including, or actually in this case, we have a less than or equal to. So indeed it does include, so that would be our closed in dot on 12. All right, so we've set up both sides, the positive and negative cases for the distance of 3x minus 6 from 0. And now we're going to add 6 to every single part of the inequality, divide every single part by 3, and we find that x is less than or equal to 6 and greater than or equal to negative 2. Again, you can re-express this on the number line. In this case, using a closed in dot to reflect the fact that our accordion, the set of values being included or covered, includes the endpoints negative 2 and 6, everything in between, nothing beyond. All right, we're almost there. We're almost to the real questions. Solve. The absolute value of x is greater than 3. Start with the easy case. Okay. So the distance of whatever is the meat, whatever is the inside, in this case it's x, from 0 is bigger than 3. So on our number line, we have that open circle, that open dot, which means we're excluding 3, but we're going all the way up ad infinitum, all the way till wherever. Because 1 hop, 2 hop, 3 hops isn't included, but anything bigger than 3 hops from 0 is included. Always got to mirror, always got to flip, look at the negative side, the side to the left of 0, and how do we find something more than 3 hops away from 0? Well, 1, 2, 3. This one's not included, but everything all the way to negative infinity is included. In this case, we find that x is either greater than 3 or x is less than negative 3. Note a number of changes here, right? So we're not including the endpoint, we're not including the value, and in this case, they're going in opposite directions. So either this way or that way, as opposed to when they're pointing in the same direction, we see the expressions combined. Okay. A brief set of review and a couple of shortcuts in thinking about positives and negatives and the signs therein, which will again come up many times in questions related to inequalities and absolute values, whether something is bigger than or less than, and how it relates to the distance of the value from 0, from that neutral center point. If we're able to simplify an expression to something like x times y is bigger than 0, so this relates to our combinations of positives and negatives. For this to be the case, oftentimes we can not do any calculations, any computations whatsoever, and just play around with, hey, what's positive and what's negative? In this case, we can set up a little chart of possible signs. Well, for x times y to be bigger than 0, to be positive, they can either both be positive or they can both be negative. Okay, if we can simplify an expression, often in quantitative comparison questions, which we'll see in just a moment, hey, x times y is less than 0, the product is less than 0, we can set up a little table, x times y is less than 0. That means they've got to have opposite signs. Either you have a positive and a negative, or you have a negative and a positive. Even just carefully identifying, not even doing the calculations, and not even sometimes picking numbers, just even identifying, hey, what are the possible signs of the values or variables we're dealing with, using the inequality given around 0, does it have to be positive, does it have to be negative, can let you beeline to the answer choice and avoid the traps. Another possibility is if we simplify an expression to get you something like x squared minus x is less than 0, or x squared, some value squared, is less than x. Now, we saw this in some of our fractions and exponents lessons together, but what this implies is that the value, in this case x, let me clear the screen. If we pull again our number line, we have 0, open circle on 0, open circle on 1. We're dealing with positive fractions, right? So if we take, for example, 1/2, and we square that, usually when we're squaring a positive number, it's going to get bigger, right? 3 squared becomes 9. However, we have this danger zone of values that are between, but not including, 0 and 1. And these are positive fractions. When we square them, what happens? 1/2 becomes 1/4. So if we visualize that on the number line, if 1/2 is the midpoint between 0 and 1, we're shrinking it to the midpoint between 0 and 1/2. So if we're able to simplify an expression to say, hey, x squared, something squared is less than that something, well, again, if x were some positive integer, 3 squared will be 9. 9 will be greater than 3. However, if x squared must be less than x, well, it must exist in this weird space between, but not including, 0 and 1. And we'll see this through countless examples of the effects of squaring or raising fractions to exponents. All right, we're going to move on to the questions. We have a couple of summary slides here, which we can come back to at the end if there's any follow-up questions. But for now, in the interest of time, we'll dive into some real GRE quant questions. As a reminder, about 7 to 8 or so of the 20 questions that comprise each of the 2 scored quant sections will be this quant comparison. This fun reasoning type question where it's always structured the same way. You're comparing 2 quantities, possibly given some set of constraints. Answer A is always bigger. B is always bigger. C, they're equal. D, I don't know. With that, off to Daniella.
Thanks, Jonathan. Hi, everyone. Let's dive into our first question here. As Jonathan mentioned, we're comparing quantity A and quantity B. The first thing that we'll notice here is that we're saying that x here is in between 6 and 7. So to echo the way of talking about this that we were talking about before, we have our number line here, okay? And we have 6 and 7, and these are 2 open dots on 6 and 7. So that means that the number goes that this equation here is represented by this number line that goes from approximately 6.000001 to 6.9999999. And that's represented by this, which goes all the way up into, but does not include 7, and begins at the number that's right immediately after 6. Now let's turn to our two quantities and the other given that's presented here. So if we look at quantity A, we see X, which is represented by this number line, over Y, which can be also written as X over 8. So here we can see we're comparing X over 8 with quantity B, which is 0.85. So what we want to ultimately understand is because X is the value between 6 and 7, we can approximate here. And we can say, is quantity A in relation to quantity B is something that's about 6 or just over 6 over 8 greater than or less than 0.85? And is the quantity that's approximately 7 over 8, what is that in relationship to 0.085? So we know that 6 over 8 is equal to 3 over 4, 3/4, which is 0.75. And we know that that 0.75 is less than 0.085. So in this case, we can see that quantity B would be bigger. Now let's look at 7 over 8 here. Now, as we all know, like through our rigorous GRE training, we're going to learn how to automatically understand what 7 over 8 is through two different ways. So one way of understanding what 7 over 8 is, I'm just going to go over here into this little box, 7 over 8. So the first way that we would know that is we'll know what all the small fractions are. And we know that 1 over 8 is approximately equal to 12.75%. Okay, or in other words, 0.1275. Sorry, not 75%. It's 0.25. Yeah. Sorry, 125. 12.5. And we know that to get to 7 over 8 is equal to 1 minus 1 over 8. So we know that 7 over 8 is equal to 0.875. So here in this case, another way to get at what is 7 over 8, we know that 7 over 8 is that 1 over 8 plus 1 over 8 equals 2 over 8, which is equal to 1 over 4, which is equal to 0.25. And what's half of 1/4? Half of 1/4 is 1/8, and a half of 0.25 is 12.5, not 12.75. It would be 0.125. I'm in percent land today. So if we're looking back over here to understand what is 7 over 8 in relationship to 0.85, we know that 7 over 8 is equal to 1 minus 1 over 8, which we established is equal to 1 minus 0.125, which is equal to 0.875. So we know that in this case, 0.875 is greater here. So A would be our answer. So because B is our answer in one scenario, or very close to it, that 0.66666000001, and that's something that's very close to 7, which is 6.99999 over 8. Because we know that they're different, we know that D, the relationship cannot be determined from the information given, because in some cases, A is greater than B, and in other cases, B here, the 0.85 is greater than A. So with that said, Jonathan, do you have anything else to add?
That was fantastic. So one overarching strategy that Daniella employed was of testing extremes, right? So Daniella was trying to prove or rule out the possibility of D, that we don't know. It could be greater than, or it could be less than, or it could be equal. We don't know. It can't be determined. So that's why Daniella picked the smallest possible value of x and the largest possible value of x within the constraint that x is between, but not including, 6 and 7. Now notice, Daniella also could have gone to the calculator, right? You could have actually computed, hey, 7 divided by 8. Not a problem, no issue. You have a calculator on screen. But again, there's many different ways to get to Rome, lots of different tools in our toolbox. Whether you're thinking of, oh, hey, an eighth is a half of a fourth. I know a fourth is always 25%, so I divide that by 2. Or we just get to know over time, 12.5% is 1/8. Then we can apply that, and then you can immediately, without even computing, spending those extra 10, 15 seconds, then you can tell me, hey, what's 3/8? Hey, what's 7/8? Hey, what's 5/8? All right. But again, one overarching theme and principle is minimum viable computation. We're actually doing as little math as possible by integrating and applying the rules in a way to determine the relationships between the two values. All right, here we're told x is not equal to 0. That's our constraint. And we're looking at quantity A and quantity B. The difference here is we have the absolute value of x plus the absolute value of -2. Immediately, as Daniella did for us, we want to simplify, translate to make it as simple as possible. So quantity A is the absolute value of x plus 2, right? Because the absolute value of -2 is always going to be equal to 2. Now, I don't know, recalling our previous framework of, hey, the absolute value of x might be x, 0, or -x, depending on if it's bigger than 0, less than 0, or equal to 0. The only thing that's precluded or ruled out in this case is the middle case. X can't be 0. We don't know if it's positive or negative. We're just first going through simplifying the expressions. X, remember, is just standing in for some number, some value. Okay, so we're comparing the absolute value of x plus 2 to the absolute value of x minus 2. So all that meat is in the absolute value, operating like a parentheses of sorts. Okay, so I would like to pick some numbers. We can pick whatever numbers we'd like. I'm going to pick 1,000. See what happens in the positive and negative case to see if we can see if D is in play. Okay, so what happens if x is equal to 1,000? Quantity A, the absolute value of 1,000 is 1,000, right? How far is 1,000 from 0? Well, it's 1,000. Plus 2 is 1,002. Again, you can pick any number you'd like. I'm just going with 1,000 because I want to. Quantity B is, hey, first, using our PEMDAS, our principle of parentheses, exponents, multiplication, division, addition, subtraction, the order of operations, which we train in a whole different lesson in arithmetic, do what's inside first. So x is equal to 1,000. So you first take 1,000 minus 2. That's 998. Then take the absolute value of 998, which indeed is just 998. So as Daniella did earlier, we're looking at these two possible flip cases. Okay, well, in this case, if x is equal to 1,000, then A is bigger. Okay, cool, so we're done. The answer is A. Move on, right? Wrong. We got to consider the other case. Remember our setup, right? The absolute value of x is equal to x if x is bigger than 0. It's equal to -x, however, if x is less than 0. And even if we didn't immediately recall the framework or the rule, when we start seeing absolute values and zeros and inequalities, positives and negatives and zeros are coming into play. So we've got to look at the positive case and the negative case. Okay, so speaking of, what happens if x is equal to -1,000? All right, well, in this case, let's look at quantity A, right? Keep it clean. Only look at quantity A alone. Well, if x is equal to negative 1,000, the absolute value of x, the distance of negative 1,000 to 0 is the positive version. It's 1,000. So it's 1,000 plus 2, which is 1,002. Again, now let's exclusively just look at quantity B, as if quantity A wasn't even on the page. Just look exclusively at quantity B for the case that x is equal to negative 1,000. Start with the meat inside the absolute value. What is negative 1,000 minus 2? Again, note how careful we have to be with our signs. Negative 1,000 minus 2 is going to be negative 1,002, right? Because it's getting more negative. It's getting smaller on the number line. So in this case, the absolute value, the distance of negative 1,002 from 0 is 1,002. So hold on, in this case, they're equal. All right, that's done. We've proved at least 2 different cases where in one case, A was bigger than B. In one case, A was equal to B. So I can't tell you which is bigger or whether they're equal. Back to Daniella.
Excellent. So let's just see here. So if P is a negative number and 0, which is less than S, which is less than the absolute value of P, which of the following must also be a negative number? So let's start out by defining what is the absolute value of P. So the absolute value of P is equal to a set of things, which is P, positive P, 0, and negative P. So within this set, let's think about this a little bit. Let's also look at the answer choices really quick and survey the answer choices. So which of the following must also be a negative number? So what do we know when we square numbers? When we square numbers, they're generally positive. So that automatically eliminates A, B, and C. So let's see here. So let's look at is P, D and E here. So P squared minus S and S squared minus P squared. So we know from this that the absolute value of P is going to be greater than S. So that means that P in general has to be a number. So let's take a number here. So let's say that the absolute value of P is that we have P, which is equal to negative 5. And that means that S has to be less than 5. So let's say S is 4. So P squared, which would be 5 squared minus 4 squared, is here. Our result here is a positive number because 5 is greater than 4. But here 4 squared minus 5 squared would lead us to a negative result. Okay, so we did that one time with 2 values. How do we know that this is indeed, that E is our correct answer? Let's check one other thing. What if P, P is a negative number. So let's try this again. And we also know that P here, because it's squared, is going to end up being a positive number. When the quantity is squared as well as when the value is squared. Let me just make this a little bit more clear here. Because P is negative, there would be a negative 5 squared and a negative 5 squared here, and the 4 is in parentheses here. So we know that this P is going to end up being a positive number here and there. So that means it would be 25 minus 16, which leads to a positive number. We don't even need to do the math. As Jonathan says, least amount of math. And here, 16 minus 25 is definitely going to be a negative number. So we know that our answer here is E.
So let's note again.
Yeah.
Oh, go ahead.
No, go ahead. It's okay. I was just going to think about another strategy, but you can go ahead.
This is great, and we're coming up on time here, so we're going to run to the next two. But note how effectively Daniella employed so many techniques and strategies, right? First, she set up the framework, defining what the absolute value of P means, and then ruled out, using the constraint, ruled out these cases because we were told, hey, P is a negative number. Then she picked easy numbers that satisfy the constraint, in this case, -5 for P and 4 for S. And also note that these are bigger than 0, right? We've ruled out the 0 case. And even before running to do any of the calculations, any of the computations, using the rules of positive and negative, the question was, hey, which has to be negative? They're not looking for a numerical answer. Daniella quickly scanned the answer choices and ruled out, without even plugging in values, 3 of the answer choices, because everything in the parentheses, the entire expression there, was going to be positive, because some value squared is positive. Some value squared is positive. That was true for A through C. She tested 2 cases for D and E and moved the heck on. All right, Daniella, can you clear this?
Sorry, a bit of a technical difficulty there. Just give me 1 second. Okay, is it cleared? Okay, great.
Fantastic, thank you. Awesome, we're running through our last 2 real GRE quant questions of the day, and then we'll wrap it up. I think this is you, Daniella.
Yes, okay. Let's read this question together. So it is given that 0 is less than x, which is less than y, which is less than 1. And I'm just going to write this out clearly, really. 0 is less than x, which is less than y, which is less than 1. And quantity is 1 minus y, and quantity b is y minus x. So what do we have here? We are saying that there's 2 numbers that are in between 0 and 1. 2 numbers that could be any place on this number line. So let's draw a number line, our handy dandy number line. And let's put 0 right here on our number line and 1 over here on our number line. And we know x and y can be in any place between 0 and 1. So what does that mean? X and y can be super, super close together. We could have 8/16 and 9/16. They could also be on our same number line, 0 and 1. 0 and 1. They could be 1/4 and 3/4. Or they could be, so we have all of these different possibilities. And I'm just going to quickly erase this here for the sake of space. But what we're going to do is to determine, because with a quantitative reasoning question, as a reminder, we always want to understand, is D in play? Can we determine the relationship between A and B? So we're going to plug in some numbers and see how things go. So let's try this easy, simple numbers of, we're going to create a little chart here as a framework. So we're going to have a chart of the value we're going to put in for X, the value we're going to put in for Y, and then our answer. Like which either quantity A or quantity B, are they one's greater than another? Are they equal? So this, I'll put A for answer. So let's plug in 1/4 for X and 3/4 for Y. So let's solve here. 1 minus 3/4 is equal to 1/4, and 3/4, which we see here as Y, 3/4 minus 1/4 is equal to 2/4, which is equal to 1/2. And here, is A or B bigger? We see here quantity B is greater. Now let's try a different set of values. I'm just going to change the color for clarity. We're going to have 1/4, let's keep it for x, and 2/4 for y. 1 minus 2/4, we get 2/4. And we have here y again is 2/4 minus x, which is 1/4, which equals 1/4. Now we're comparing quantity A to quantity B, and we see here that A is greater. So here, because we have B is greater in one scenario and A is greater in another scenario, the correct answer choice must be D. I think that Jonathan has do you have something to share as well about the accordion nature of this problem?
Totally. Yeah. And that was fantastic. And again, there's lots of different tools in our toolbox that we can present and solve in many, many different ways. So Daniella showed us the example of setting up, again, these two cases that both satisfy the constraints, but picking those extremes, right? Are they closer or are they further apart? So testing extremes, picking easy numbers, and seeing if D was in play. One alternate way is just to visually reason. So if we use our number line, again, and we know that, hey, x and y exist somewhere between 0 and 1. We don't know exactly where. Let's take a look at the quantities first. Like, what are we being asked for visually? Well, 1 minus y, right? We can either interpret that numerically as some value, or visually, using our distance and our hopping mechanism. Well, 1 minus y is like, how far is y from 1, right? That's what the subtraction means. So like, how many little hops do we have to take to get to y? Okay, what's y minus x? Well, y minus x is just like, how far apart are x and y? What is the distance? How many hops do you have to take between x and y? So one way I like to visualize it, without even picking numbers, without even doing any calculations at all, is using the principle of testing extremes, but just visually representing it on the number line. So I might think of two different number lines, right? We're between 0 and 1. It is conceivable. It satisfies the constraints of 0 is less than x is less than y is less than 1 for x to be here. I don't even care what the value is for y to be here. And then literally all I'm comparing is this area to that area. That's what the two quantities mean. That's what numerically they translate to visually on the number line. Here's my second number line. I'm testing the other extreme. They're either possibly really far apart. They could also be really close together. It's relevant because those are the two quantities I'm comparing. I don't even care what the values are. Again, I'm comparing this area, this distance, to this distance. So like an accordion, the distance between the points can shrink or expand depending on where they are. So I'm comparing the blue to the green as standing in for quantity A and quantity B, and clearly I can see I have no freaking clue because I satisfy all the constraints I'm given, I make no unwarranted assumptions otherwise, and I beeline to D. Whether, and you can also, as you go through practice, right, we tend to be more meticulous and write down more and do more computations earlier on in our practice. And then by the time you get to test day, you might either visually depict it on the number line or even see that accordion in your mind. But we want to make sure that we get the accuracy up as high as possible before we move on to strategies and approaches that might shed some seconds here and there. Lots of different approaches to get the same result, but noting again, we have all those tools in our toolbox. So in the interest of time, all these questions are of course available for free online. We would highly recommend to you, if you haven't yet, take a free practice test online, an official GRE practice test. Download the GREmax on tablet or mobile. Sign up for a free 20-minute consult with a GREmax team member. We're more than happy, as always, to stay on even after this call to see how we can be of most help to you in your particular grad school dreams. Again, noting the diversity of different programs and ways people are using the GRE, even just amongst Daniella and myself. Lots of different ways you can make it work for you. We're also, of course, really excited to share our tutoring Packages, where you can work one-on-one with us. We spent countless hours getting people amazing results, getting into top programs across the country and really seeing a market improvement. You can take a look at the details of the packages online on GREMax or on the app as well. But we would love, love, love to work with you and help you unlock your fellows' potential, because there's really no ceiling other than the one you set for yourself. So with that, we're going to thank you so much for joining us this evening. Look forward to seeing you next time. And again, happy to stay on to answer any questions whatsoever. Thank you. Let us know again. We're here for you. So if you have any questions or thoughts about your grad school application process, let us know. All right, well, with that, you can always reach out to us over email, schedule a call. But thank you all so much. Have a wonderful evening.